All right, so this is going to be, I'm going to go through the answers here the best that we can. Hopefully get through all of it. We should be able to. Anywho, the first question is asking about what we know about a neutron and how we know it. And when you read through these particular questions, hopefully you noticed that they were that tricky kind of question where it was like two answers are very, very similar, and another two answers are very, very similar, and then you had to figure out which is which. So I'm going to kind of walk through what it is that how I did that. So in this instance here, it says A says a neutron has a mass of 1 atomic mass unit when scientists tested the masses of elements with equal protons and did not balance. So there had to be a particle that had mass but not a charge. B was a neutron. Oh, this is the one that's very similar. B says the neutron has a mass of 1 atomic mass unit. When science tested the mass of the elements, there was equal protons at balance, so there had to be a particle that had a mass but not a charge. So what I noticed here is that equal protons, there we go. Equal protons did not balance. Equal protons, it did balance. And then we'll go on to the next one. C says neutron has negligible mass because scientists tested the masses of elements and equal protons and it did not balance. So there was a particle that had mass. Neutron has negligible mass because scientists tested the masses of elements. And actually, what happened here is that the negligible mass ones automatically should have been a red flag that those weren't the correct answer, because we know that you should know that the neutron has a mass of 1 AMU. So then which one of the above answers is the most correct one? The most correct answer is A. That's how they figured that out. Scientists know that a proton has a what type of charge, and then how did they know that? So the first thing that we should probably identify here is the proton has a positive charge. And how do we know that? Well, the gold foil experiment is how they figured it out, but basically the researchers or the scientists observed that the positive alpha particles that were shot at the gold foil some of them bounce back. Oh, spelling is hard. Indicating there was a positive nucleus. So something about them, the alpha particles bounce back, the alpha particles were repelled, something along those lines is what we're looking for. These two questions, the first one would be worth 1 point, the second one would be worth 2 points, one for correctly identifying the positive charge, and one for having some type of explanation that makes some logical sense based on what we learned in class. Identify the following statements as proton, neutron, or electron, some combination of the both. The element that has a positive charge would be the proton. The thing that contributes to the mass number would be the proton, but also the neutron. Is located outside the nucleus would be the electron, and as a negative charge would also be the electron. Being located inside the nucleus would be the proton, and the neutron. Is being neutral in charge would be the neutron, and having negligible mass would be the electron. The way that we're going to grade these is each column is going to be worth a point. So this would be 1 point. The neutron column would be 1 point, and the proton column would be 1 point. And it's kind of all or nothing on those. So next one, you had to get out your handy dandy periodic table. This looks something like Oh, I gave Jethro away, so this is Jezebel. Maybe you named yours Sam. Maybe you named yours Jenny. Maybe you named yours Rutherford. I don't know. But in any case, I located element Cl on the periodic table. Element Cl on the periodic table is chlorine, and chlorine has an atomic number of 17. I also remember from this particular situation that the atomic number is equal to the number of protons that an atom has. So in this instance, I'm going to tell myself that the number of protons is 17. And in a neutral atom, the number of electrons equals protons. So neutral atom, number of electrons equals number of protons. So that's going to give me my number of electrons here is also going to be 17. If I want to figure out the number of neutrons, I might do some math, and that math might be mass number minus protons, right? So in the case of the number of neutrons for chlorine, I'm going to take the mass number, which is 36, minus the number of protons, which is 17, and that should give me my neutrons. And so 36 minus 17 is, what is that, 19? Right there. Next one. I see that I have an element that has 20 protons, and from what we just discussed, protons are equal to the atomic number, so that's going to give me an atomic number of 20. We also have no other evidence to support that this isn't a neutral atom, so this is going to also be 20. And when we want to calculate our mass number, is equal to protons plus neutrons, right? So in this instance down below, I'm going to take my protons, which was 20, plus my neutrons, which was 21, to get my mass number, which in this case is 41. Now, I also needed to use the handy-dandy periodic table to locate the element itself, and I used the atomic number for that, and I found out that the element in question was calcium. Good for your bones. All right. Next situation, especially based on what we have up on top here, says consider the following elements and identify which ones are isotopes of one another. What I do know from what I've just written up above is that I've got 21 protons. My atomic number tells me the number of protons. I've got a bunch of neutrons. I got 22 neutrons, 22 neutrons, and 20 neutrons. And the only bit of information that I don't know in this case is the number of protons, it looks like, of scandium. So again, I'm going to grab Jezebel here, and I'm going to go ahead and take a look at the scandium. And it's going to take me 85 minutes to find scandium, which is a lie, because scandium has is element number, atomic number 21, which that tells me that I have 21 protons, which tells me that the pairs of atoms that are isotopes of one another are atom 1 and atom 3. Okay. How do I know this bit of information? Well, I know that isotopes have the same number of protons, but different number of neutrons. So there you have it. That's how I knew. Now, the next situation, you're supposed to take the information given and write it in nuclear notation and or hyphen notation. So to refresh your memory, because I had to refresh my memory this morning, nuclear notation is mass number over atomic number. And then we have our element. And hyphen notation would be, I should kind of do one of these guys right here, would be the element and then mass number. So for the nuclear notation for the first one, I'm told the number of protons, which is the atomic number from our information up above, so I'm going to put 29 down here. To get our mass number, we have to remember that we add protons and neutrons, so I'm going to take 29 plus 26, and that's going to give me my mass number, which I believe is, 15, carry the 1, 55. And then I'm going to go ahead and identify which element it is using my good periodic table friend Jezebel here. And the atomic number for 29 is copper, apparently. So we're going to throw a Cu right there. We're also going to write the hyphen notation right away. So we're going to take copper, and then we're going to use the atomic number, which is 55. And then for the next one, we're given an atomic number of 48, which tells us the number of protons. So I'm going to put that right down there. And then to figure out 48 plus 60 neutrons is, if I did my math right, I believe it's 108 atomic number or mass number. And when I go on to the handy dandy periodic table, I look for element 48, which is somewhere in this general region right here, which happens to be cadmium. And so in this case, it would be cadmium 108. Yep, that's a thing. All right, so how are we doing here? So far, so fantastic. All right, so now we have some other information. So we're figuring out here that we are told that sulfur has 16 protons. We are told that sulfur has 18 neutrons, like so. And you're asked to identify sulfur's average atomic mass. So sulfur's average atomic mass is, I'm going to locate sulfur in the periodic table. Sulfur is element 16. Element 16 is sulfur. That's average atomic mass is 32.07 AMU. And how did I find it? Looked on Jezebel, the periodic table. Note that I did write AMU. Please be in the habit of writing those things, even though it's technically not right there, but it's fine. Now, so what is sulfur's mass number? I have to remember that in order to get the mass number, I add protons and neutrons, right? So I think to kind of like remember what's going on here, I'm going to take protons plus neutrons. Oops. And that's going to give me my mass number. And then I'm going to take the number of protons that I was given, which was 16. And then the number of neutrons that I was given, which is 18. And that's going to give me my mass number, which is, 434. And again, AMU. Note that I did that there, right? 8, 34. Yeah. All right. So how are we doing here? Okay. I can calculate the average atomic mass from the relative abundance of isotopes and masses of individual atoms. Okay. You might remember that the formula for average atomic mass was relative abundance, rel abun, times atomic mass. Nope, that's not right. Times mass number. plus rel A bun, relative abundance, times mass number. And so I'm going to figure out that I have a mass number of 10 and a mass number of 11. And I have a relative abundance of 19.9, which I need to change to a decimal, so 0.199er, and 80.1, which I'm going to change to a decimal, 0.801. So I'm going to go and add these, or fill in the blanks here. So I'm going to take the 0.199er times 10 AMU plus the relative abundance again, which was 0.801 times 11 AMU. And I'm going to do some calculating. So 0.199 times 10 is 1.99. And 0.801 times 11 is 8.811. And when I add all of that business together, I get a value of like 10.801. We said you should go to 2 decimal places, so it's going to become 10.80 AMU. Please put AMU there so I don't have to take points away from you. I don't enjoy doing that. Next one. You're using the graph to do the same thing. So here we go. We have our relative abundance. So I'm gonna set my formula up again. So we have rel A bun times mass plus rel A bun times mass. Okay. So I see that this graph is giving me my relative abundance. So that's 61%. So it's going to become 0.061. 39% is going to become 0.39. I do have 2 mass numbers. I have a 69 atomic mass units and 71 atomic mass units. So I'm going to plug in my stuff. So in my formula, I have 0.61 times 69 AMU. And I have, 0.39 times 71 AMU. So I'm going to calculate again. So 0.61 times 69, I get 42.09 AMU plus 0.39 times 71. So that's 27.69 AMU. So that plus the 42.09 gives me 69.78 AMU. Remember, AMU. And then I'm going to use the handy-dandy periodic table, the wonderful Jezebel, to go ahead and find which element this is. And the element that has a mass of 69.7 something is gallium, which melts in your hand and also in your mouth. So, but we don't want to eat it. All right. Fission-fusion reactions. What type of reaction releases energy? Holy buckets, they both do. What type of reaction requires the input of a neutron? That would be fission. And what type of reaction combines 2 atoms to make 1 atom? That would be fusion. Okay? Now, next one. Fission or fusion? Sounds like a game show. Welcome to Fission or Fusion. On this day, we're going to figure out which is which. The first one is fission, or is fusion, though. I know that because it looks like I got 2 things combined to make 1 thing. I also remember that when I'm balancing these equations, I need to make sure that my numbers match up. So the 13 and the 16 have to equal whatever's on the other side. So I'm going to take 13 plus 16, and that's going to be 29. So that's going to go up here. I'm going to take 6 plus 8, and that's going to be 14, and that's going to go down here. I'm then going to go to the handy-dandy periodic table and identify element 14, which is silicon. Which, by process of elimination, some of you are going to say, well, then clearly the next one has got to be fission. And we shouldn't live our life by the process of elimination. Sounds like a terrible plan. But in reality, what really this should be setting us off here is the presence of the neutron. Okay, so in this case, both sides have to add up to the same value. So I have 6 and 7. So 6 plus 7 is 13. So 13 minus 1 is 12. So I'm going to have a 12 on top. On the bottom, I have 3 and 3. So 3 plus 3 is 6. And 6 minus 0 is 6. So that's going to be a 6 down there. And then looking at the periodic table, I see that that's carbon, atomic number 6. Woo. All right. Then we have, during alpha decay, what is always produced? Well, a positively charged helium is always produced. During beta decay, what is always produced? Well, a negatively charged electron is always produced. During gamma decay, what is always produced? Well, electromagnetic radiation is always produced. Too fast? Are we good? All right, now we need to figure out what's going on here, alpha or beta decay. Well, based on what we just discussed, this one is going to be beta decay. How did I know? There's an electron present. And both sides have to add up, right? So in the case of the mass number here, 89 has to equal, well, 89 minus 0 has to equal 89, so I'm going to put an 89 on top. I don't like how I wrote that. Now, 38 plus, nope, not plus, minus a negative 1 is going to be, bless you, 39. So that tells me that it's element 39, which happens to be yttrium. So that means that we are left with alpha decay. And in this instance, both sides have to add up, but the presence of the helium is the thing that gave this away. So I'm going to look at the relationship between 31 and 4. 31 minus 4 is 27. 15 and 2. 15, oh gosh. 15 minus 2 is 13. And that tells me, 13. And that tells me that the element in question is going to be aluminum. And that is the answer key for your practice quiz. We are going to have a real quiz on this tomorrow. Have a wonderful day.